Hello again, everybody. From this point on, we are going to treat the electron using quantum mechanics. So, which is why I'm calling this as the quantum electron, as opposed to what we did in the last few lectures when we treated the electron classically first and then semi-classically. Let us recall that the behavior of our electron in the quantum mechanical sense is governed by the Schrodingers equation. We should also recall that what we today call as quantum mechanics is really the result of the work of a lot of people. It's due to Niels Bohr, Heisenberg, Schrodinger, of course, de Broglie, Wolfgang Pauli, Paul Dirac, and so forth. Let me write down what we today call as the Schrodingers equation. So there it is. The stuff in the square brackets is what is called as the Hamiltonian. You see, quantum mechanics works in a very strange way. You have an Hamiltonian operator which operates on this thing called the wave function, which in our case is over this. That's our wave function psi, and this is the Hamiltonian operator over here. When the Hamiltonian operator operates on this wave function, it provides us an energy E multiplied by the same wave function. So this is, in a mathematical sense, basically an eigenvalue problem. You take an operator, operate on a function, you get some constant scalar times the same function. So that's an eigenvalue problem. But let me also note that the equation that I've just written down here, this is what is called as the time-independent Schrodinger's equation. What Schrodinger actually originally wrote down was the time-dependent Schrodinger's equation, which was essentially a differential equation that involves both position and time. In the first derivative of time, it involves basically the first derivative of time and the second derivative of position. There is an interesting story behind that, which we will not get into. So that's the time-dependent Schrodinger's equation for the electron, which is essentially a wave equation. We have seen wave equations before when we talked about elastic waves. So this is the wave equation for the electron, the time-dependent Schrodinger's equation, which actually can be simplified through a series of steps to leading us to the time-independent Schrodinger's equation, which is what I've just written down. Okay, so that's the time-independent Schrodinger's equation. That's something we want to bear in mind. Now, Schrodinger actually wrote this equation down in order to explain the behavior of this electron in hydrogen. So, spectroscopic information was available for hydrogen, and then the results were rather puzzling. Right? It indicated that our electron can take on only discrete energy levels, minus 13.6 divided by n squared eV, where n is an integer. Any positive integer. So the lowest energy that the electron can take on in hydrogen was minus 13.6 eV, and then the next higher level was minus 13.6 divided by 4 eV, and so forth. So one of the first triumphs of the Schrodinger's equation was to explain this rather curious behavior of the electron in hydrogen. But of course, the same equation could be used to handle a lot of other more complex situations, such as other elements which contain more than one electron. Of course, some modifications had to be done, and we will briefly look at that today. And soon after that, people were able to address molecular problems as well. So he could also explain the behavior of electrons in molecules. And soon after that, behavior of electrons in solids. That led to band theory, which is really what we're going to dive into in this particular course very soon. It led to band theory. It allowed us to explain why certain materials are metals, certain materials are insulators, some in between, semiconductors, etc., etc., etc. It was very revealing, right? So the Schrodinger's equation was a huge triumph in explaining condensed matter phenomena. And more recently, this whole area of quantum mechanics has been exploited to a fairly high level within material science, right? One can use this theory to actually make quantitative predictions of various properties of various materials in a very versatile and quick manner. Now, that is a subject of a completely different course, so we are not going to touch on that in this series of lectures. What we're going to do now is to try to understand certain basic features of this particular equation that I've just written down, the time-independent Schrodinger's equation. Note that, again, I've indicated what the Hamiltonian is. It's the stuff in the square brackets. There are two terms in there, right? So the first term represents the kinetic energy, and h bar, as you know, is a Planck constant, and m is the mass of the electron, and del, the del operator is a differential operator, so del squared in 1D is nothing but d squared over dx squared, and in 3D it's d squared over dx squared plus d squared over dy squared plus d squared over dz squared. Right? So the del squared operator is nothing but a differential operator. So that's the first term which represents the kinetic energy. The second term, V of r, represents the potential energy. Right? So the Hamiltonian is really the sum of the kinetic and the potential energy of our system. Bear in mind that although I've been talking about electrons here, this equation applies not just to electrons. Right? That's a beauty. It's a very general equation, and by suitably choosing our model system and suitably choosing our potential V, this can be used to handle many different types of problems, and I will mention a few shortly. Okay, so our first step is to try to understand some basic features of this Schrodinger's equation. So we will try to address how free electrons behave and what we can learn about free electrons from by using the Schrodinger's equation, right? So since our electrons are free, or it can even be particles, it doesn't have to be electrons, right? So free electrons are free particles. Let's say they are completely free. If they are free, then the potential V is zero, right? It's a constant, first of all, and it's zero. So there is no potential energy trying to bind our electrons in any particular place. So our electrons are completely free, the potential is zero, and so that term gets knocked out of the Schrodinger's equation, the time-dependent Schrodinger's equation. And let's see what happens beyond that. Okay, so for our free electrons or particles, we set V equals 0 in our time-independent Schrodinger's equation. So this term here gets knocked out. And we're going to consider a 1D situation, our favorite. And so our spatial variable is x, and our del squared function quantity becomes d squared over dx squared. Right? So we have this equation over here. Now, as before, we suggest a solution for our wave function psi of x. Right? We suggest that our wave function psi of x equals e to the ikx, and we substitute e to the ikx into both sides of our one-dimensional Schrodinger's equation for free particles. And let's see what happens. Let me make myself a little room. So we get that. So essentially, the second derivative of e to the ikx gives us I squared times k squared. I squared is minus 1, which takes care of the minus sign on the left hand side. So we get plus h bar squared k squared over 2m times e to the ikx equals the energy times our suggested wave function e to the ikx. Of course, the two ikx can be cancelled out, right? And then we are left with E equals h bar squared k squared over 2m. Now let's make a very important observation. This is our energy E, which is equal to h bar squared k squared over 2m. Since our electrons or particles are completely free, the only energy that our particle has is kinetic, right? It's all kinetic energy. If it's all kinetic energy, then it has to be equal to 1/2 mv squared or p squared over 2m, right? Where p is the momentum. if our energy is all kinetic and it is equal to p squared over 2m, which according to our Schrodinger's equation is also equal to h bar squared k squared over 2m, then p, our momentum, should be equal to h bar k, right? So let me write this down. So there it is. So p has to be equal to h bar k for all of this to work out. In fact, this is exactly what de Broglie had originally suggested, in fact, the Schrodinger's equation was constructed so that this result would be recovered. So it is no accident or no coincidence that we are getting this result. Now, let me also make another very important observation. Now that we know P equals h bar k, we now know because of this that the velocity of our electron is related to the reciprocal space quantity k. Remember, k or q is something we have dealt with in the past when we discussed lattice waves, and we discussed phonons and the phonon band structure and so forth. So the reciprocal space quantity k is showing up again, right? And when we discussed Fermi surfaces a couple of lectures ago, we also transformed our energy space to a velocity space, and I plotted the situation of electrons in a velocity space, and at that time I noted that the velocity space is equivalent to the reciprocal space we've been discussing all along. So here is a very clear mapping. So our momentum p, or velocity times mass, is actually equal to h bar k. This is going to be very useful as we go forward. Let us ask an interesting question at this point. So we now know that for a free electron described by e to the I kx as the wave function, the momentum is given by h bar k. But where is the electron? Right? What is the position of our electron? We know its momentum, but what is its position? In order to do that, we need to invoke another quantum mechanical principle, and that is that we can only talk about the probability of finding an electron at a particular position, and that probability is given by the modulo square of the wave function. So if the modulo square of the wave function is the probability of finding an electron at a position x, for our electron, for our free electron, this probability is equal to 1, because the modulo square of e to the I kx is equal to 1. What does this mean? This basically means that our electron is equally likely to be found at any position x, because this probability is not dependent on x anymore, x you see, and it's equal for all values of x. So which basically implies that our electron is equally likely to be found anywhere in space. This is actually Heisenberg's uncertainty principle in action. So the position of the electron is completely uncertain. It could be equally likely to be anywhere in space, which is the hallmark of the electron being completely free, right? It's totally free. It can be anywhere it wants. But the momentum is fixed precisely. The momentum is known precisely. So the momentum is known precisely, and the position is completely uncertain. So this is we are actually having a glimpse of Heisenberg's uncertainty principle, right? Now, using appropriate values for our potential V, and I'm going to go back to our time-independent Schrodinger's equation for a second. Okay, there it is. So by using appropriate values of V, we can solve appropriate problems using the Schrodinger's equation. So when V equals 0, we have the free electron or free particle situation, which we just saw. What if we have a particle in a box? So the particle is free within a box, but it cannot leave the box. Now that situation can be represented by its own potential. Let's say we have a 1D box, of length L. So our particle can be inside this 0 to L region, but it cannot go outside. So the potential corresponding to this situation is something like this. So we have a potential V which is 0 from x equals 0 to x equals L, and the potential is infinite everywhere else, right? So this potential is really constraining our particle to be inside the box of length L. When we do that, we have a series of solutions, and I'm not going to go through that right now. I'm just going to leave that as an exercise. I recommend that you take a look at a basic quantum mechanics book where this problem is very nicely handled. So this is called the particle in a box problem. Another problem that can be solved using this Schrodinger's equation is the harmonic oscillator problem, right? So for that, what one would do is to choose again an appropriate value for the potential V. The appropriate quantity for the potential V would be 1/2 kx squared. Bear in mind, this k now is not our reciprocal space k. The k here is the spring constant, right? And x is of course the position. So 1/2 kx squared represents the potential energy corresponding to a spring, a harmonic oscillator. In fact, Schrodinger actually solved this problem when he first proposed the Schrodinger's equation as well, in addition to the hydrogen atom problem. So when you stick in 1/2 kx squared for V and go through the solutions, you will get the solution of the harmonic oscillator problem, which again is something we are not going to work out over here. I recommend that you take a look at a basic quantum mechanics book again if you are curious about the solution. In each of these cases, particle in a box as well as a harmonic oscillator problem, you will get quantization of energy levels. You will find that there is a infinite number of solutions for the wave function. There are a lot of possibilities for the wave functions, and corresponding to each wave function is a value of energy. So there is a spectrum of energy and wave function solutions to both of these problems. In fact, this is one of the features of an eigenvalue problem. An eigenvalue problem in general has a large number or infinite number of solutions. And the solutions always come in pairs, right? You will have an infinite number of e's and infinite number of psi's, the wave functions, and each e is associated with a particular value of particular choice of psi. So our particle in a box problem and the harmonic oscillator problem will lead us to a spectrum of solutions, a spectrum of energies, and these energies will all be quantized, right? Now, with all of these things in mind, we move on to the hydrogen atom problem, right? And again, I'm not going to solve this problem in its entirety. Once again, I'm going to refer you to a basic quantum mechanics textbook. What I'm going to show you is really the final outcome of solving the Schrodinger's equation for the hydrogen atom problem. For the hydrogen atom problem, we have to choose our V appropriately, right? So our electron in our hydrogen atom is actually bound to the nucleus through electrostatic forces. So the potential energy of our electron is going to be determined by that attractive interaction between the nucleus and between our electron. So I'm going to scroll ahead, make myself a little room, and then we are going to address the hydrogen atom problem. So the hydrogen atom is of course the simplest of all atoms. It contains one electron orbiting in quotes of course around our nucleus. There is a historical reason why we are looking at the hydrogen atom. First of all, it was the first atom for which the Schrodinger's equation was solved quite satisfactorily. And the second reason, of course, is because it is the simplest of possible atoms. And as I note here in this slide, it is a 3D problem with spherical symmetry. So you So these are two important aspects. So we're going to write down the Schrodinger's equation, and we're going to keep in mind that it is a three-dimensional problem. We have our electron going around our nucleus in a three-dimensional sense. So we cannot reduce this problem to a 1D problem, unfortunately. So it has, but it has spherical symmetry. So we are going to exploit the spherical symmetry in this problem. I have just written down our original Schrodinger's equation, the time-independent Schrodinger's equation, and I've written down the pieces of the Hamiltonian as well in blue, right? So since this is a three-dimensional problem, our del squared operator is d squared over dx squared plus d squared over dy squared plus d squared over dz squared, right? So that reflects the fact that it's a 3D problem. And our potential V is, as I just noted, the attractive interaction between our electron and the nucleus. If our nucleus has an atomic number Z, then this attractive interaction between our electron of charge E and our nucleus of charge ZE is given by the expression I've written down over here, right? So negative indicates attraction, Z is the atomic number, and epsilon naught is the permittivity of free space, right? And note that because of spherical symmetry, the denominator has the modulo of R. What really matters from the point of view of this Coulomb interaction, attractive interaction, is just the distance between our electron and our nucleus. So throughout it is assumed that our nucleus is fixed at the origin, and the position of the electron is basically R, the R vector. But it's only the scalar, the magnitude of R, that matters from the point of view of this attractive Coulomb interaction, right? So the kinetic energy operator or the del squared operator is given by this, and our potential energy of our electron bound to our nucleus is given by this. Of course, in the case of the hydrogen atom problem, Z is actually equal to 1, but we're still going to keep it because it's going to be useful later on, right? So this is it. So this problem can be solved analytically, and it will give us the answer for the hydrogen atom problem. And Schrodinger did that. Schrodinger did that in his paper in 1926. There are a sequence of laborious steps involved, but it can all be handled completely analytically, right? To give you a glimpse of the complexity of this differential equation, I'm just going to write down the differential operator, the del squared operator in spherical polar coordinates. So this is what happens if you now trade off the Cartesian coordinates for spherical polar coordinates. Now you must be wondering, why did Schrodinger do this? The Cartesian choice appears very reasonable and compact and simple, but the spherical polar choice makes it fairly complicated. But the point is, believe it or not, transforming the Cartesian to spherical polar is actually an enormous simplification from the point of view of an analytical derivation. Remember, these were the times before the advent of things like MATLAB and Mathematica and so forth. These were pre-computer days. So scientists had to be very creative as to how they would handle problems. They had to come up with tricks, mathematical tricks, exploit mathematical tricks and so forth to solve problems of this type. And there is a certain beauty and elegance also when you go from Cartesian to spherical polar, especially for a system that displays spherical symmetry. So anyway, so when you write your del squared operator in this manner, using spherical polar coordinates, it also turns out that you can factor out your wave function psi. Remember, psi is a function of r vector, which means psi is a function of x, y, and z, or psi is a function of r, theta, and phi. And so the wave function can actually be factored, and when you take that factorization as well as this del squared operator in spherical polar coordinates into account together, you get enormous simplification, and you're able to reach the solution. That's essentially what Schrodinger did. Now, we are not really going to go through all the gory details of it. Again, I'm going to refer you to a quantum mechanics book, but I'm just going to highlight some of the important milestones. So here is what I just said. Our wave function is a function of three variables x, y, z, or r, theta, phi. And because of that, it turns out that we can factor our wave function psi into three pieces. One depending on r, the second one depending on theta, and the third one depending on phi. And when we stick this into our Schrodinger's equation along with our choice of the spherical polar coordinates for our del squared operator, it turns out that our differential equation gets broken up. It factors into a couple of differential equations, and so each of them can be solved analytically. Now I'm going to give you a glimpse of the solution, right? I'm going to write down what kind of results you would get for R, capital R, capital theta, and the capital phi functions, right? So I'm just going to write that down. First, the angular part, right? The theta and the phi dependence. It turns out that the theta and the phi dependence of the wave function can be written in terms of Legendre polynomials, right? So the capital A is some constant, which we will worry about later, which can be set up based on normalization. And what is really important is the theta and the phi dependence. So the capital P function is the Legendre polynomial, which is a function of cosine theta. And the phi dependence is contained in the last piece, e to the plus minus I m phi. Now, note that there are two integers here, L and M. These will eventually become our quantum numbers, right? So L is our angular momentum quantum number, you may recall this, and M is a magnetic quantum number, right? So L and M are integers, which means we have a spectrum of possible solutions for our theta and phi dependence, right? A series of Legendre polynomials and a series of e to the I m phi function. So M is an integer, right? Now the P, it turns out that the product of the Legendre polynomial and the e to the plus minus I m phi can be combined together, and it's called a spherical harmonic. So Y represents the combination, the product of the Legendre polynomial and e to the plus minus I m phi, and it is called the spherical harmonic. So Y is a function of theta and phi, and it has the two indices L and M, which are both the integers, and they represent two types of quantum numbers, the angular momentum and the magnetic quantum numbers. So that's the angular dependence, right? That's the theta and phi dependence. Now let us take a look at the radial dependence. So here is our radial solution, right? And again, capital B is some constant, which is not important at this point. What is really important is the dependence on the radius. So you have a e to the minus r over n a naught. A naught is a constant. It's called the Bohr radius. It has dimensions of length, and it's 0.53 angstrom. And n is an integer, which we call as a principal quantum number. Right, so now we have already introduced three quantum numbers, right? The principal quantum number, the angular momentum quantum number, and the magnetic quantum number, N, L, and M. And okay, so that's the first piece of our radial solution, and then the second piece has R, the radius to the L, where L is of course our angular momentum quantum number, and the last piece of a radial solution has another special type of polynomial called the Laguerre polynomial, which is represented by capital L, and it's a function of the radius, right, and the principal quantum number. Now these indices n plus L and 2L plus 1, these basically indicate the type of the Laguerre polynomial that should be used. So you see the solution the final solution of our Schrodinger's equation for the hydrogen atom problem has the r, theta and phi dependence, and the dependencies are all pretty complex, but it can be analytically done. So what I'm trying to do here is to show you a glimpse for how complex this entire solution process must have been, but it can be done. That's the beauty of it. So we thus have the wave function, which is a function of three variables, r, theta and phi, and there are also three quantum numbers. These quantum numbers are of course integers, but there are limits on what their values should be. Let's briefly take a look at that, and let me write that down. So those are the possible values. Our principal quantum number can take on any integer value, any positive integer value, 1, 2, 3, etc. Our quantum number L can range from 0 to n minus 1, and finally our quantum number M can have values of 0, plus minus 1, etc. Up until plus minus L. So the maximum value it can have is plus L. So those are the limits on the possible values our quantum numbers can take, but there are three of those, right? Now the next question is, what about the energy? We now have the wave functions, but of course, as I mentioned earlier, each wave function is associated with a certain energy value, right? No, of course, note that you have infinite number of solutions here, because n can go on from 1, 2, 3 all the way to infinity. So infinite number of wave functions, infinite number of solutions, and so there should be a corresponding spectrum of infinite number of energies, one corresponding to each value of n, l, m triplet. Right. So let me jot that down. So our energy E, which is to which we tack on the three indices L, M, and N, corresponding to our three quantum numbers, has this form: minus m, the mass of the electron, times charge of the electron E to the 4 divided by 8 epsilon naught squared, h squared, n squared, where epsilon naught is the permittivity of free space and h is of course the Planck's constant. So that is the result for our energy, and bear in mind that there is no dependence on L or M. Our energy is purely dependent on just the principal quantum number n. Now everything else in the energy expression other than n squared are universal constants, so we can evaluate them, and when you do that you get the answer minus 13.6 divided by n squared eV, like in electron volts. So our energy of our electron in the hydrogen atom can take on only these values, minus 13.6 divided by n squared. So when n equals 1, of course you get minus 13.6. This is the energy of the 1s level, you will recall, right? So that's the lowest energy level. At ground state, when our hydrogen atom is not perturbed, its electron is going to be at that energy, minus 13.6 eV, meaning you need to supply 13.6 electron volts to pull that electron, that 1s electron, out of hydrogen. Now, to just get a view of the wave functions that are involved, I'm just going to write down the first few wave functions for the first few choices. But actually, before we move on, I want to make the note that the traditional way of writing the indices beneath the E is N, L, M. So I made a little error here, which I'm going to try to fix. So here are the wave functions for some of the lowest energy electrons, energy levels. So the first one, this one over here, is for a principal quantum number n equals 1 and the other quantum numbers are 0. Right? That is our familiar 1s orbital, and note that its wave function is purely a function of r, the radius. Right? A0 is of course the Bohr radius, which is a constant. There is no theta or phi dependence for this 1s function. So if you go to the next quantum number, and of course before that I should note that for n equals 1, the only value for the other quantum numbers, the L and M, are 0 values. So there are no other values possible based on the limitations that we wrote down just a little while ago. When we move on to n equals 2, now L and M can take on a few different values, right? One such set of values is are 0 and 0 for L and M. So that gives us the wave function for n equals 2 and 0 values for L and M, and that is our familiar 2s orbital, right? So that's the 2s orbital. And this also is a function purely of the radius. There is no theta or phi dependence. So the 1s and the 2s orbitals, consistent with what we would have learned earlier, are purely radial quantities with purely spherical symmetry. No theta or phi dependence. When we move on to other values of the L and M integers, L and M indices, quantum numbers, corresponding to a value of 2 for the principal quantum number, n is still equal to 2. Now L and M can take on other values other than 0. That is. So we get 3 possibilities, right? So when n equals 2, our L quantum number can take on values of 0 and 1. The value of 0 corresponds to this quantity over here, and the value of L equals 1 corresponds to all of these. When L equals 1, note that M can take on values of -1, 0, and +1. So those are the 3 indicated over here. This bar 1 is really a -1. So those are the 3 functions corresponding to n equals 2 and L equals 1. That leads us to the familiar the p orbitals, px, py, and pz orbitals. And note that these 3 orbitals now are functions of r, theta, and phi. Well, the pz orbital is just a function of r and theta, whereas the px and py are functions of r, theta, and phi. Now, I'm not going to show you pictures of these orbitals. For that, I refer you to quantum mechanics book, or there are several locations on the internet where you can go and picture these wave functions. So those are the wave functions for some of the low-lying energy levels. Note that because the energy is purely a function of just n, right? The energy of all of these 3 levels, these 3 wave functions in hydrogen are equal, and given by minus 13.6 divided by 4, because n equals 2. Okay, so we are going to finish up this lecture with a very brief summary of quantization, right? If you recall, in this lecture we started off by writing down the time-independent Schrodinger's equation, and then we tested that against a very simple example of a free particle or a free electron, and then we moved on to just noting that the particle in a box problem and the harmonic oscillator problem can also be solved using the same Schrodinger's equation with suitable choices of the potential. And then finally we moved on to the hydrogen atom problem, and although we did not explicitly solve it, we provided highlights of the milestones through the solution process. So what I'm going to do right now is very briefly show you the results of this quantization process. Okay, so these are the 3 problems for which we are going to very schematically represent the solution. First, particle in a box. As I noted earlier, the potential outside the box is infinity for this case, and V inside the box, the potential inside the box, is equal to a constant value which is 0. The solution for this problem, if you work through the math, is that the energy is going to be proportional to n squared, where n is an integer. Right? So energy is proportional to n squared. So how does the spectrum of energy look like for this case? So here is how it looks. So since E is proportional to n squared, where n is an integer, our spectrum of energies look like this. As you go to higher and higher energy values, the energy allowed energy levels start spreading out because E is proportional to n squared. So that's the situation for a particle in a box. For a harmonic oscillator, we have to substitute the potential to be 1/2 kx squared, if you recall. In other words, our potential is proportional to x squared, right? And it turns out that that's a parabolic potential, and when you have a parabolic potential of that type, the solution for the energy is that it's proportional to an integer n. So here is what you have for our harmonic oscillator. V is proportional to x squared. The solutions are proportional to n. One nice little tidbit to bear in mind here is that there is something called the 0-point energy, which actually shows up in the solution of the Schrodinger's equation for the harmonic oscillator problem, which basically means that even when n equals 0, your energy is actually not equal to 0. It turns out to be 1/2 h bar omega, where omega is the frequency of the oscillator. And for all other values of n, of course, the energies are all equally spaced, because you see energy is proportional to n. For the hydrogen atom problem, we have already seen this a fair amount. One thing I neglected to mention in the previous slide was there was a bunch of normalization constants sticking up front when I wrote down the wave functions, and those are all basically just constants fixed by the requirement that the modulo square of the wave function should be equal to 1, meaning each of the wave functions has to be normalized to 1. That fixes those constant values. But anyway, in the case of the hydrogen atom problem, we stick in a Coulomb potential that is proportional to 1 over r, minus 1 over r, because it's attractive between the electron and the nucleus. And when we do that, we get a solution for the energy which is proportional to minus 1 over n squared. So that's the situation for the hydrogen atom. So there it is. For our hydrogen atom, energy is proportional to minus 1 over n squared, and so the energies the energy levels become more and more closely spaced as you go up in energy, because of the proportionality to 1 over n squared. So that's the story in a nutshell for these three important and simple examples: particle in a box, harmonic oscillator, and hydrogen atom. The potentials for each of these cases have been drawn as per the quantities used in the corresponding Schrodinger's equation, and of course the energy levels are shown, making it clear how the quantization works in each of these three cases. Our next step is going to be to deal with atoms with more than one electron. In other words, we are going to graduate from the hydrogen atom to larger atoms, and immediately after that we're going to talk about systems containing more than one atom, namely molecules. So we're going to graduate from atoms to molecules, and soon after that it's going to be, of course, solids. Thank you.